Okay, so natural logarithms. Natural logarithms are all about logarithms that have a base of e, just like common logarithms are logarithms with a base 10. So the symbol that we use for a natural logarithm is ln, and you can use a capital Ln or a lowercase ln. And I know that's weird because it's natural logarithm, not logarithm natural, but I think they just started with L because log starts with L. Whenever you use natural log or see natural log, it just means that it's a base E logarithm. So that's the biggest concept you have to understand about today, is the natural log of any number or variable really is equivalent to log base E of that number or variable. And because we use base E for so many types of problems that grow or decay continuously, and that's why we have a special logarithm for it. But all it really means is log base E. All the properties of logarithms that we have learned apply to natural logarithms as well. And remember, that's because a natural logarithm is a logarithm. So for example, anytime we see log base B of 1, we know it's 0 because it's really saying b to what power would equal 1. Well, it's going to be the same thing when you see a natural log. If you see the natural log of 1, that really is just equal to 0. Now, even though you don't see it there, guys, you got to remember that anytime you see natural log, it's just known to be base E. Just like if you see log of 1, it's known to be base 10 if it doesn't have the little subscript there. So anytime you see natural log of 1, the answer is just 0. Same thing for the next one. Log base B of B equals 1 because B to the first power equals itself. So it's the same thing if you see a natural log. If you see the natural log of E, that is also just 1 because that's really saying E to what power equals E. Because remember, even though you don't see the little subscript there, it's known to be there. The next two properties are just our inverse properties. If we do a log of an exponential, they undo each other, and vice versa. If we do the exponential of the log, they undo each other. So these properties also apply to our natural log. If you see natural log of E raised to the x, it's just x. They undo each other. Or if you say E raised to the natural log of x, it's just x. So anytime you see E to the natural log, it undoes it, or anytime you see the natural log of E to some power, it undoes it. All right, a rule for natural logarithms that we see quite a bit, which we already have up here, is this one. Anytime you see the natural log of E, it's just 1. And we just explained why, but that's important because a lot of times when you're solving problems, you'll end up with a natural log of E in there. And it's kind of like you can just kind of ignore it because it's really just saying times of 1. All right, so just like we did with our exponential and logarithmic equations to start off with, we're going to rewrite the equivalent exponential and logarithmic equations for each one. So this first one is exponential, but since it has base E, instead of saying log base E of x equals 15, because you're never ever going to see that, we're going to use natural log. That's the whole point of having a natural log. It's anytime we have a base E problem, we know we're going to use natural log instead. So we would say the natural log, you do not write the subscript, it's known to be there. Base E of x equals 15. Anytime you say natural log, it's automatically known to be base E. All right, so the next one we would say the natural log of 45 is equal to 3x. Again, we know to use natural log because it has a base of E. So the next one, two, are logarithmic equations, and we want to rewrite them in exponential form. So remember, even though you don't see it there, because this is saying natural log, it is naturally a base of E. So this is really saying E to the x power equals 20. And then the last one would have been E to the 9.6 power equals 4x. All right, so recall, we just talked about these above, log base B of B to the x equals x, and B raised to log base B of x equals x. These are our inverse properties. So look at A right here. It says the natural log of E raised to the third power. Automatically, you would do the natural log of the exponential, so they undo each other, and the answer is just 3. Another way you can look at this problem is we can use our law of logs to work it out. If we have the natural log of E to the third power, we can use that product property that allows us to take that power down to the front and make it the coefficient. Or if we do that, this then becomes 3 times the natural log of e. And recall this important rule for natural logarithms, the natural log of e is always 1. So that's just 3 times 1, which is ultimately 3. So that's just another way that you can look at this problem, but it's easier just to apply the inverse property, and it's a one-step problem. So try the next one. Okay, so for this one, we should be getting 42 because that is that second property over here. Anytime you have e raised to the natural log, and it doesn't even matter what's in here, let's say it's a big old heart right there, they undo each other, and we just get the heart out. So e to the natural log of 42 would just be 42. All right, so now let's get into solving some equations. So starting with this first one, this is an exponential equation because the variable is in the exponent. We don't see logs in here anywhere. So the first step we learned from the last lesson is to isolate the base. And in this case, our base is by itself. So the next step is to take the log of each side. But in this case, because it has a base of e, instead of taking the log of each side, we're going to take the natural log of each side. And it'll save us from having to do so many steps. So the natural log of e to the x is equal to the natural log of 3.2. Now, from here, we can just apply that property that any time we have the natural log of e raised to the x, it's just going to give us x. Look back up here where we talked about this, because they undo each other. So if you know that, that just saves you some steps, and you can just say, okay, well, that's x equals the natural log of 3.2. On your calculators, you will see that right above your store button is the natural log button. And you also see that if you press second natural log, it's the e raised to the x. So these go together because they're inverses of each other. So all we do is we press the natural log, and then we would type in 3.2, press enter. And normally with these, we round to 4 decimal places. We're going to get for this one, x is approximately 1.1632. If you ever have a problem and it says give the exact answer, this would be the exact answer right here. And then if it says approximate the answer, this would be the approximate answer right here. Sometimes on calculator inactive problems, because you don't have a calculator to type in the approximate answer, they will just ask for the exact answer. All right, on the next problem, because it's got some multiplying and adding over there with e to the x, the first step is we must isolate the base. Okay, so to do that, we're going to start by getting rid of any addition or subtraction. So we're going to subtract 3 from each side. So that leaves us with 5 times e to the x is equal to 15. And then we would divide each side by 5. And we get that e to the x is equal to 3. Now we're back to a problem like we just worked out. So now that we've isolated that base, we're going to take the natural log of each side since the base is e. We can apply our inverse property right here. The natural log of e to the x just leaves us with x. And if we pop the natural log of 3 into our calculator to get the approximate answer, it would give us approximately 1.0986. Now, when you do have technology and it's calculator active, you can always check your answers too. What I can do is after I've figured out what the natural log of 3 is, I can then store it. If you just hit store, it'll pop up the answer for x. Press enter, and then I can go back and check my equation by retyping it in. 5 times e raised to the x power plus 3, and if we did this correctly, it should come out to equal 18. And it does, so we've checked it and we know we did it. Okay, so problems A and B were exponential equations. Problems C and D are logarithmic equations because the variable is inside the logarithm. So the first step is to always condense your logarithms if you have more than one. In this first one, we do not. So since it's just one logarithm, we can go ahead and base it up. Because this is a natural logarithm, the base is e. So we're going to e it up on each side. I know that sounds funny. It sounds like we're saying eat it up, but we're going to e it up, base it up. So that way, on the left-hand side, that e raised to the natural log, they undo each other, and that 3x just pops out. But on the right-hand side, we are left with e to the second power. Then we would divide each side by 3. And if it wanted the exact answer would be e squared divided by 3, or 1/3 times e squared. If it wants the approximate answer, then go type that in your calculators, and that would give us approximately 2.4630. On this next problem, we have a logarithm plus a logarithm. So remember, the first step is you must combine the logs first before you can then base it up on each side. I like to make sure the logarithms do not have coefficients, because if they do, we have to pop them back up as the powers, and in this case we don't. So since this is addition, we're going to multiply. So this is going to be the natural log of x times 2x equals 2. So that is the natural log of 2x squared equals 2. Now we're going to e it up on each side because we have to base it up to solve this. On the left-hand side here, that e to the natural log cancels each other out, so we're left with 2x squared equals e to the second power. We would then divide each side by 2, so that's going to give us x squared is equal to e squared divided by 2. And then last but not least, we would take the square root of each side. Now remember, anytime we're using the square root property, we should always put plus or minus. So that is plus or minus e squared divided by 2. Okay, but remember, whenever you have logarithmic equations, you always have to take your answers and substitute them back in and make sure you're only taking the log of positive numbers. So in this case, if we were to substitute that negative 1.9221 into the original equation, it would not be allowed in the domain of that problem. So therefore, our final answer is only the positive answer. So it only be 1.9221. You do not have to check it when it's originally an exponential equation, but we do for a logarithmic equation. Okay, so this next one is another exponential equation. This one's a little bit tougher because it has e to the x in a couple of places. And here's the problem with this one. I accidentally typed it wrong, so I need y'all to fix a part real quick. Right here, that should have said 2e to the 2x. I'm sorry I did not catch that. What happens on this one is it has a quadratic pattern. It's kind of got that trinomial pattern where you have that squared term, and then that linear term, and then the constant term. So to help you see that, I'm going to rewrite this. This is really saying 2 times e to the x squared plus 5 times e to the x to the first power minus 12. And that's what we mean by that quadratic pattern. You have that squared term, and then that linear term, and then that constant term. So what we're going to do is factor this, but when we factor it, instead of factoring it with like just an x, we're going to factor it with e to the x. So we can see right here that if we have e to the x and the leading coefficient's 2, one of them must have been 2e to the x and the other one must have been e to the x. And then we have to sit there and do our magic and figure out, well, what factors would work here so that it multiplies to negative 12 in the back, multiplies to 2e to the x squared in the front, and then has that positive 5e to the x. So some of us are really good at factoring, and we can sit there and use our multiplication tables and figure out that's going to be negative 3, that's going to be positive 4. If you struggle seeing that, what I would suggest doing is doing what we call a substitution method. Come over to the side of your paper and go, all right, let's let y, and I would pick a variable other than x since this problem has x in it. So let's let y equal e to the x. And then I would rewrite this trinomial with y instead of e to the x. So it would look like this. 2y squared plus 5y minus 12. And then I would factor that trinomial. Now, at this point, hopefully most of y'all can guess and check because that one's not that difficult. If you still need to do it the long method, that's fine, but I can go ahead and tell you you're not going to see me do that often because we need to be able to factor pretty fast. If we do use the long method, 2 times negative 12 is negative 24. The numbers that multiply to negative 24 and add to positive 5 would be negative 3 and 8. So we would then break this up. That is 2y squared minus 3y plus 8y minus 12. And then we would use grouping. The first two terms right here have a y in common. And we're left with 2y minus 3. The next terms have positive 4 in common, and we're left with 2y minus 3. So our common group is 2y minus 3, and our other group is y plus 4. Once you get your factors, what you do is then when you come over here to rewrite them, you know it's not really y, it's really e to the x. So you would substitute the e to the x back in for y to write our factors. Okay, so we had to do that in order to isolate the base. When we see that quadratic pattern there, that trinomial, that was the only way to be able to isolate the base. So now, like we do with any factoring problem, we set each factor equal to 0. So we have 2e to the x minus 3 equals 0, and e to the x plus 4 equals 0. So for the first one, we add 3 over, 2 e to the x equals 3. We divide by 2, e to the x equals 3 halves. At that point, we would take the natural log of each side. So the natural log of e to the x equals the natural log of 3 halves. And the natural log of e to the x is just x. So our final answer on this part would be the natural log of 3 halves. And I will tell you, I've seen a problem like this several times on the final exam, and normally they leave it like that. They do not actually put it in the calculator. But of course, you could put it in your calculator to check your answer and make sure it worked at the end. For the next one, we would subtract 4 over. So we get e to the x equals negative 4. Well, guys, if you recall what we learned earlier in it about the graph of y equals e to the x, remember I told you it was really important that you learn this graph. It's right between the graph of y equals 2 to the x and y equals 3 to the x. Well, something we know about this basic exponential function is its range is all positive real numbers. It never equals 0 and it never equals a negative number. So if you recognize that when you get here, it's impossible for e to the x to equal negative 4 because it's not in the range of that problem. But let's say you don't notice it and you just are rolling with it and you go ahead and you take the natural log of each side. So we have the natural log of e to the x equals the natural log of 4. So on the left, that just gives us x. Well, then you have the natural log of negative 4. And we also know that's not possible. We can't take the log of negative numbers or 0. And the reason why we can't is because the domain of a logarithm is the range of the exponential. So these connect right here. So in this case, again, that was not possible, that was not possible. So our final answer would only be the natural log of 3 halves. And the cool part is, not that you'll always have technology, but if you do have technology when doing a problem like this, you can always store that in your calculator and then retype the equation and make sure it comes out equals 0. Where if you stored natural log of negative 4, it would automatically give you an error because you can't do that. And for this particular course, since your final exam is calculator active, that's a good strategy to use for those types of tests. All right, so let's look at the next one. What is the inverse of f of x equals 1.5 raised to the x plus 4? Okay, well, guys, this is an exponential function. So immediately you should know that its inverse should be a logarithmic function because that's the whole relationship between exponential and logarithmic functions. All right, let's go back through our steps for how to find an inverse. So remember, we know that f of x really means y. So when we switch these, I'm just going to put y in there, and then we'll rewrite it with the correct notation at the end. So step 1, we're going to switch x and y. So this is going to become x equals 1.5 raised to the y power plus 4. Then we're going to solve for y. So the next step would be to subtract 4 to the other side. So we have x minus 4 is equal to 1.5 raised to the y power. So there's 2 ways that you could then do this. One is you could change it from exponential form to logarithmic form. If you do it that way, what we would do is we'd say, okay, we know this is going to be a log equation, so we're going to say y, which is our exponent, equals log, the base is 1.5 of the answer, which was x minus 4. And if you do that, then all you have to do is rewrite it with your correct functional notation. The inverse of f of x is equal to log base 1.5 of x minus 4. All right, the other way to do it is how we've been solving logarithmic equations, which is where you take the log of each side. So if we did it that way, we would say, okay, that is the log of x minus 4 equals the log of 1.5 to the y power. By doing that, that allows us to take that power and drop it down to the ground. That's that third law of logs that helps us solve exponential equations. So we end up getting log of x minus 4 is equal to y times log of 1.5. So then to get the y by itself, we would divide each side by the log of 1.5. Now you'll notice that when you do this, these answers look different. And this is why it is so important that you learn change of base formula. Technically, these are equivalent, but what may happen is you might be taking a standardized test and it's multiple choice, and you only see this as an answer. Well, if you solved it this second way, you need to know how to take log of something divided by log of something and rewrite it using change of base. And so that's why it's so important for y'all to learn change of base formula. So at this point, we need to recognize, oh, okay, if I'm going to rewrite this with not common logarithms, that would be log, whatever is in the bottom is the base, base 1.5 of x minus 4 is equal to y, which we would then rewrite using our correct functional notation. So again, to get from this step to this step, all we did was use that change of base formula. Okay, so we're going to work on this practice in class, and then we will pick up with the modeling part in the next lesson. We're going to spend 2 days on this lesson.